The next talk is by Fernando Aiube from State University of Rio, talking about commodity prices. Thank you.
Okay, thank you, Rafael. This is a joint work with Bruno. She is a master's student at the Faculty of Economics. And she was supposed to be here, but she had health problems, and so I'm presenting her work. So to model commodity prices, there are two different approaches. And basically, we can divide between structural models that are based on rational expectations, dynamic programming, and theory of storage. And factor models, which are exogenous factors describing the term structure of commodities. Well, under these factor models, which is this case we are studying, there are a lot of works. And from the beginning, with works of Bruno and Schwartz, 85, Schwartz, 97, that study commodities modeling through one factor. In this case, spot prices is the state variable used to model the commodity prices. Two-factor models, there are more works on this direction. Gibson and Schwartz, 90, Schwartz 97, Pilipovic 97, Schwartz and Smith 2000, Gammon, Nguyen, and Hexbro and Jaimungal, among others. I'm mentioning just a few works on this direction. We can say that the work of Gammon is a little bit of a mix between structural models and factor models, because they use inventory information to model volatility, and then they use this on dynamics of the spot prices. And the work of Hexbro and Jaimungal, it's much more in the, not describing the term structures, but also pricing spread options on power derivatives. The three-factor model, we can mention Schwartz and Schwartz and Smith, also Cortázar and Naranjo, and many others factors describing this term structure. So the relevance of this kind of models are for pricing derivatives, option on futures, spread options. Moreover, commodities traders use this model to hedge their positions, and portfolio managers use these models to allocation of their assets. Companies also price their projects using real options, and this kind of pricing their projects is dependent on the model you choose to describe the prices. Also, regulators use models to study limits on trading, mainly in case of agricultural commodities that have impact on the inflation because of food prices, etc. So here is the basic definition of convenience yield. Convenience yield is the benefit that accrues to a physical trader, owner, and do not to the owner of a future position in the market. Based on no arbitrage condition, we can write that the future is the spot price, times the exponential, including here the cost of carry or the convenience yield, which is the y here. So if we extract this convenience yield from this equation using two contracts, we can write that the convenience yield is, the implied convenience yield is based on this on this formula. And if we plot this convenience yield based on these two futures contracts, we can see a noise behavior of this convenience yield. So models which are based just on a constant convenience yield are far from the real behavior of the convenience yield, who is much more stochastic than a constant. So a quotation from Gaiman: the convenience yield has become in recent literature a popular state variable for explanation of different shapes of forward curves. So many models use convenience yield to describe the behavior of these forward curves or future curves. So back to Gibson and Schwartz model, it's a two-factor models. It's a two-factor model, and the first factor is the spot price. It's a geometric Brownian motion. And the second factor, the convenience yield, is a Ornstein-Uhlenbach process. And alpha is the long-term average of the convenience yield. So both Brownian are correlated. And using the fact that the future is the expectation of in a Q measure of the spot price at the maturity, you can write the model for the future prices, who is a fine function of x and y. And then the model is calibrated using this formulation. So the idea here is very simple, what we are done. We want to improve this, we want to go deeper in this describing the convenience yield without including any jump component or without including any stochastic volatility. So this would make the calibration much more complicated. So the idea here is to explore more the convenience yield dynamics without making assumptions about models which would have much more problem to calibrate. So one idea is to look, the long average of the convenience yield is not a constant, but it has a dynamics. And in this dynamics, is also a Ornstein-Uhlenbach process. So we are going now use this three-factor model. All the Brownians are correlated. And then in the same way, using the future as an expected value of the spot price, we can derive the logarithm of the future as a fine function of the spot prices of the convenience yield and the long-run average of the convenience yield. So now, what you're going to do is to calibrate both models, two-factor and three factors, and we're going to measure the performance of these two models. So, to this end, we took 5 contracts, future contracts, of oil prices, WTI oil prices. And then we proceed. This is the observed variable that we are going to use in the calibration. Then we calibrate both models. Here I'm presenting only the state variables for the three-factor models. We extract the state variables of this calibration procedure. Here we have the spot prices in black. In red, we have the convenience yield. And in green, we have the third factor, which is the long-run average of the convenience yield. I'm not going to exhibit the same for the two-factor models, but the behavior is similar. So here we measure the in-sample error between the calibrated price and the observed price. So in some vertices of the curve, we have error that is greater in this Gibson two-factor model of Gibson-Schwartz two-factor model, and in some cases we have a greater error in the three-factor model. But on average, both models, on average, three-factor models here has a less mean error, considering all the contracts. So here we can see the first contract. Sorry. The first contract of this calibration procedure. This is the blue line, which is hidden by the first contract filter. This is the model, the first contract of the model. We calibrate. This is the two-factor model. We can visually observe that the three-factor model has a better fit to the first future contract. So here is the two-factor, and here is the three-factor model. So what we are going to do next is a work in progress. She doesn't finish her work, but we are going to calibrate out of the sample errors to see the performance. But we expect that the three-factor models would have a better performance in out of sample also. So here we have the term structure of future prices in this day, July 2005. You can see here the three-factor model is the green curve. You can see that's the first contract is we have a greater error. We have another term structure for this day on April 2011. Here the future prices on the fifth contract is greater, but the first contract here we have a less error, a smaller error for the three-factor models. And more recently, we have a position of backwardation of the future prices. And we can see also again that the first contract is better just for the three-factor model. So there are a lot of implications for this kind of studies. One of these implications we're going to show you is the hedging implications. For example, it's common in the industry to have long-term commitments. And we want to hedge these long-term commitments using short future contracts. For example, here we have the long-term commitments maturing on time capital T, and you want to hedge this position with short futures contracts. So in this case, the sensitivity of the future commitment to the state variables, the present value of this sensitivity should be the sensitivity, the sum of the sensitivity for each contract to the same state variable. And then we can solve, for example, this system and compute the omega, which is the long position in the future contract. The number of contracts in this for each maturity we are using to hedge this future commitment. So in our case, when we are using short-term contracts to hedge long-term future contracts, it's important to have accurate position of the model for the first maturity. And you could observe that the three-factor model have a more accurate position, and this would this would be better to use this kind of modeling to make this kind of hedge, which is very common in the industry. So there are other types of application of these models for pricing, and a lot of other cases we could show, but to save time, we are going to focus on this hedge. Here we are using convenience yield, which is important variable for describing the storable commodities term structure. Unlike the two-factor models that is a constant factor, we are using a dynamic to describe this behavior. So these results exhibit a smaller in-sample error, and mainly in the near maturity of the contracts. And these have implications for pricing and for hedge long positions with short maturity contracts. So that's all.
Thank you very much. We have time for, actually, been even fast, so we have time for a couple of questions. Yes.
So in the calibration, what methods did you use for calibrating Kalman filters?
Yes.
Did you try ensemble?
Yeah, it's a fine model. It's a fine model. In Gaussian model, so the usual procedure is to use Kalman filter. You use this procedure here.
Was it fast? And how long does it?
It was for three-factor model. It takes a little bit time, but anyway, it's for accurate position. There's no problem here. The problem would be if we introduce here jump components or stochastic volatilities or something like this that would make the use of Monte Carlo methods that would be much more computer expensive.
Any other? Yeah.
So, Fernando, I remember that, if I remember correctly, I think Sebastian has a model which is a stock vol model for futures. And you decided to make the mean stochastic, not the volatility. And would you have any any rationale for that? I mean, what to take you to choose those factors rather than stock vol that seems so much in vogue at some point?
The problem we think is to make the estimation or the calibration more simple. It would take much more time, and it's if you use particle filter or MCMC, so this is much more time expensive to make this calibration. So we decide to make things simple and use Gaussian models to use Kalman filter. That's the main idea. If the things are all Gaussian, we can stay using Kalman filter.
And from a practical point of view, do you see there's any difference between those models in terms of performance? I mean, performance in the sense of fit the data.
The three-factor model is better in this analysis. We have also run this for copper prices. The same, we got the similar results for copper, and we guess this is much more precise mainly for applications, for hedge applications and pricing applications.
Okay, thank you.
we can move to, thank you very much, and let's thank again Fernando.